Developers are aggressively moving to multimodal AI models to ingest and analyze massive libraries of raw video data. But pushing this much media through an API is causing production budgets to rupture. Teams are seeing sudden, inexplicable spikes in their billing dashboards that defy their initial projections. These side-by-side video inputs share the exact same duration, frame rate, and resolution. The left is a stable color block. The right has static visual grain. Run through an AI, the grainy footage generates an exponentially higher token count. The processing requirement explodes. Standard logic suggests that video resolution and duration dictate the final API cost. Treating a language model like a traditional cloud storage bucket completely ignores how these systems actually parse data. In information theory, entropy is the mathematical measure of randomness within a dataset. Algorithms do not see noise as useless interference. They read randomness as high-density information. A perfectly clean digital vector signal is highly predictable. A noisy, real-world physical recording is chaotic. The AI lacks the mechanical ability to distinguish between a person intentionally walking across a frame and the random snow of a low-light camera sensor. It treats every flickering pixel of static as a unique data point, assigning it the exact same computational weight as a human face. This algorithmic confusion directly attacks the model's core efficiency mechanism, spatio-temporal compression. Often, the resulting data density is completely invisible to the human eye, disguised as a cinematic aesthetic or a minor compression artifact. Therefore, your final API bell is directly tied to a file's visual and auditory entropy, not its total runtime. We can see the mechanical precedent for this in early cloud gaming platforms. To maintain a stable, low-latency stream to the user, these platforms employ a strict bitrate cap, usually around 15 megabits per second. Rendering a clean, flat 3D wall texture in a virtual environment is highly efficient. The compressed data occupies minimal space within the pipeline. If you activate a film grain filter, that data block instantly expands, hitting the absolute ceiling of the pipe's capacity. The constant fluctuation of thousands of pixels forces traditional video encoders to abandon predictive compression entirely. They must encode every single point of noise. That exact same failure loop is now overloading the token counters in modern neural networks. Modern multimodal APIs rely on vision transformers, or VITs, to process imagery. When a VIT ingests a video frame, it breaks that frame down into a grid of distinct spatial patches. If a patch contains a solid color, the model is highly efficient. Those adjacent grid squares merge into a single, highly compressed data token. Put that same silhouette in front of a tree with thousands of fluttering leaves, and the system faces independent, chaotic movement. Because every leaf moves independently, the grid cannot consolidate. The spatial patches shatter into hundreds of distinct, separate token blocks. The transformer also runs inter-frame tracking, evaluating the footage at intervals of a 30th of a second. If an object remains completely static between those frames, the model saves resources by simply reusing the existing tokens. When thousands of patches are constantly shifting, they fail to compress spatially in the single frame and fail to compress temporally across multiple frames at the exact same time. The transformer generates a massive surplus of tokens just to describe background data that holds zero analytical value. High visual complexity mathematically dismantles the cost-saving architecture of the vision transformer. In production environments, this unnecessary token generation is driven by three specific types of visual noise. The first is high ISO sensor noise and artificial film grain. The AI mistakenly tracks these shimmering pixels as thousands of tiny individual moving objects, forcing it to generate a continuous stream of temporal mapping data. The second is highly complex, fluttering backgrounds that surround a primary subject. The third is unstabilized, shaky camera movement. A shifting frame forces every pixel to move constantly. This completely prevents the model from reusing tokens from previous frames, breaking temporal compression entirely. When you combine a shaky camera, a complex background, and a grainy sensor into a single clip, the resulting token bloat compounds exponentially. Every piece of unchecked visual entropy translates directly into a lost operational profit margin for developers. This entropy problem also extends to the simultaneous audio processing layer running parallel to the video. This diagram shows how the model runs an internal speech-to-text layer by plotting a continuous spectrogram of the audio track. Persistent background hums, like server fans or distant traffic, actively populate that spectrogram with dense data. Multimodal APIs charge you to parse this auditory texture, even if it contains 0 spoken words and 0 analytical value. Ambient room noise acts as a continuous, silent drain on the multimodal token budget. To control these data costs, you must build a dedicated FFmpeg pre-processing pipeline to sanitize your files before they ever touch the LLM API. This flowchart outlines the cleaning funnel. First, an aggressive AI denoiser flattens irrelevant textures to save spatial tokens. Next, a digital stabilization pass deshakes the footage, maximizing inter-frame token reuse. Finally, a strict audio noise gate drops all non-speech frequencies to a flat line. If your analysis only requires tracking a specific subject, you can apply focus crops or artificial background blurring to actively remove the remaining spatial entropy. Pre-processing is not an optional quality control measure. It is a mandatory requirement for maintaining sustainable unit economics in multimodal AI.